Drummond. I've been here for 5 weeks, and I counted, and I think about 75% of talks mentioned cosmic rays. So that's clearly relevant to this meeting. And I'm here just to facilitate basically a pub brawl, and I'm going to give you, first of all, a quick 10-minute crash course. Get it? Yes. Thank you. And basically explain why cosmic rays are important feedback agents. And then after 10 minutes or so, we are going to dig into some of these questions, and you're the customer. You can tell me what you want to talk about, but some examples, I'll just read off the slide. The big elephant in the room is how exactly do cosmic rays drive galactic winds? What is the primary mechanism controlling the energy dependence of cosmic ray transport? Do cosmic ray driven winds overproduce gamma rays? And if they do, what does it tell us about transport processes? What's the contribution of cosmic rays to the CGM pressure, something we talked about during this workshop? How important are bottlenecks, if you want to talk about this new and exciting topic? Can we use small-scale experiment by looking at individual objects to put constraints on transport? What's the relative role of cosmic rays and radiation? So only recently did we really get excited about the impact of cosmic rays, but prior to that there was obviously tons of discussion about radiation-driven winds. We can also talk, I don't know if we'll have time for this, but we can talk about the role of cosmic rays in AGN feedback. So all of these topics, basically, all of these questions that we can address essentially boil down to this question of cosmic ray transport. So think of this, obviously relativistic particles like photons. For photons, we have an idea how they propagate and what their opacities are, but for cosmic rays do not. So it's kind of like if you were trying to build a star without really knowing what the opacities are. Here we're trying to build models of galaxies without knowing really how cosmic rays propagate through this medium. If you ever get lost, all answers to all of these questions are in this article. So it's just a shameless advertisement. Just a short article of 237 pages that we published last year. All right, so the clock starts now. I'm going to kind of try to put everybody on the same page, and I will give a super quick, ridiculously quick overview of why cosmic rays are important and how they are related to turbulence. So you might have seen this. This is a very long parallel describing distribution of energies of cosmic rays. If you calculate, there is only about 1 cosmic ray per billion particles in our galaxy. So why bother? Why do they matter? Well, they are fundamentally important because energy density in cosmic rays, despite their scarcity, is related or comparable to turbulent energy density. So here it is, I said it, turbulence, right? They cool relatively slowly. They can heat the gas and ionize it, and they are relatively well coupled to the thermal plasma. They are important across the whole range of objects from supernovae or from dwarf galaxies to AGN. In our galaxy, they are produced by supernovae. When they are produced by some Fermi-like process, they eventually escape and begin to propagate, and spend quite some time in the galaxy, something on the order of 30 million years, during which they cover about 10 megaparsecs by zigzagging through the galaxy. And you can use this to compute some baseline number for the diffusion coefficient, which is 10 to 28 centimeters squared per second. And in the supernova proper, this is significantly suppressed by various non-resonant instabilities, such as the Bell instability. However, once you get out, the transport is very different, and it's basically driven either by scattering on external turbulence. So here is your turbulence again. This is so-called extrinsic confinement model, or they scatter on fluctuations that they produce themselves. And so a lot of thought went into this last process, and it works kind of like this. So you have gyro radius that is much smaller than the fluctuation in the magnetic field, and you basically slide a bead on a wire. If the fluctuations are much smaller than gyro radius, you don't see these fluctuations. But when you're in the middle, there is a resonance that, if you calculate Lorentz force, it gives you a coherent force acting on this gyrating proton from this alphane wave. And so people have been discussing this process. In this case, you don't change the energy of the particle, but you can change the pitch angle, the angle between magnetic field and velocity, and you can scatter particles in a pitch angle. This is a nice visualization from NASA that illustrates this. So as a result of this pitch angle scattering, you can basically isotropize the particles in the frame of the wave. And if cosmic rays want to go faster, then they will have to lose momentum on average. They will lose energy. That energy will be pumped into the wave energy of these waves shown in blue, and subsequent dumping of this energy will hit the gas. So this is pretty much all I wanted to say about this instability. You can regulate the amplitude of these fluctuations by introducing a number of damping processes. And we don't have time to go into this, but I'm just going to say you can damp these fluctuations produced by the streaming instability by, for example, nonlinear Landau damping, turbulent damping, or ion neutral damping. I think Yves mentioned this yesterday, or dust damping. The bottom line is that we can actually have a combination of streaming and diffusion. You can actually move faster through space than streaming would dictate. Okay, so this was 5 minutes, and this is related to one of the first open problems, which is how exactly do these cosmic rays drive winds in galaxies. So just one more or two more slides to illustrate exactly what I mean by this, and then we can open the floor and have a fight about this. So this is density as a function of height above a disk, and you have a balance here between gravitational force and pressure force due to cosmic rays. Now, perfect balance, right? And now we go back a slide or two and introduce the relative motion of cosmic rays with respect to the gas, this transport process, streaming or diffusion. And this happens. Cosmic rays stream out and they start interacting with lower density gas. Acceleration due to cosmic rays wins over gravity, and you can drive an outflow. And we've seen this many times in, or at least signatures of things that seem to look like winds driven from galaxies. And before we talk, I just want to leave you with this provocative statement here that you can define an Eddington limit for cosmic rays. So you take, this is going to be the only derivation here, and I'm really done after this slide, then we talk. You take flux of cosmic rays, you express it, for example, in terms of diffusion. So diffusion coefficient times gradient of cosmic ray pressure. And you want to balance this by gravity, right? This is essentially going to give you an Eddington limit, just like you would get in the case of radiation. It's just that you replace photons, one type of relativistic particle, with cosmic rays. So analogous expression for Eddington limit would have Thomson scattering cross-section. Instead, we have here diffusion. And the reason I'm showing you this is because for the case of cosmic rays, if we were to just plug in a constant diffusion coefficient here, as people very often, or used to do at least, then low density gas will have a lower Eddington limit. So it would be easier to drive an outflow in the case of cosmic rays. In the case of radiation, you could imagine that photons could zigzag their way out of the galaxy through these low density channels. Here, under this assumption, it would not happen. So that's the contentious part here. You can describe this in terms of this ratio of Eddington limits due to cosmic rays and radiation in terms of mean free paths. I'm not going to bother you with details, but basically, this is much less than unity, which in this simple example suggests that cosmic rays could drive winds pretty effectively. So I'm done with talking, and so back to this question of how exactly cosmic rays drive winds. People build careers around this topic. It clearly depends on what this transport coefficient is, or method of moving cosmic rays around. And so here is, for example, a list of representative simulations, and they are paired such that so as to kind of emphasize the difference that you get depending on the physics of transport. This is obviously, I may be extremely biased, but this is from my own paper. It shows what you have when you include transport, when you drive the wind, versus when you don't include transport. In both cases, you have cosmic rays. So I'm done talking. This is question number one. How do cosmic rays drive winds? I have some examples from other people's simulations. Once we are done with it, we can talk about other questions that I have on that list. But if somebody wants to steal a mic and tell us where we should go, then please go ahead. This is the moment.
Well, if we want to describe the cosmic ray ability to drive winds, we need also to take into account the properties of turbulence.
Right.
And as you showed in your simulations, that there is an importance on the alpha and Mach number. Yes, and it changes a lot. So this, I would tomorrow also discuss that there could be some additional changes of this paradigm, and it's related to the alpha and Mach number in the subalphinic turbulence. And this is can, according to whatever we have, only increase the effect of the alpha and Mach number on this outflows.
Yeah.
No, it's okay. Go ahead. Go ahead.
So the discussion is about feedback formally, but you also showed the spectrum. Is it true that you basically can ignore the whole spectrum because it's all low energy cosmic rays, and you can say that yes, the streaming is the main mechanism, etc., etc.?
Yeah. So this is an energy dependent statement. When you're where bulk of cosmic ray pressure is, which is about GeV cosmic rays, then you are quite likely in the regime where transport is dominated by streaming instability as opposed to turbulence, probably. At very low energies, cosmic rays are important for well, maybe not necessarily driving the winds, but for changing the thermodynamics of the gas by heating individual. We're changing basically chemistry of the ISM.
Mm-hmm. Okay, so another short comment. So your electron luminosity is a spherical galaxy. Is it possible to derive some for this
just like people who do disks, they have spherical cows as well, right?
So you have estimate for this galaxy? Is it the same or?
No, this is just a basic, back on the envelope estimate. Just to make a point that this could be important, but how exactly what the relative ratio is, that's the whole name of the game.
Just to follow on.
Are you going to say something relevant? Maybe Elliot will just touch on that.
Oh, I'm sure that what I'm going to say is less relevant than his, so you go ahead and then I can wait.
Please go.
Yeah, please go ahead.
Go on the line and then I will.
No, I was just going to make the point that I think there's this hypothesis that streaming is important at low energies and something else is important at high energies. But if there is extrinsic turbulence, it can, in principle, rather easily supply a sufficient scattering rate that it makes the distribution function at GeV energies so isotropic that there is no streaming instability.
Yes.
So I think one should be careful about assuming that streaming is as dominant at low energies as much as I love it. I think it's actually quite unclear whether that's true or not.
I think you're a mind reader because the next slide is specifically about that point. So this is going to be a nice segue to the next point before we hear the next question.
Okay, so you will explore this issue of the transport coefficient, right? How it may depend on the other processes.
Yeah.
Okay.
Right.
But before that, I would like to make a question because regarding cosmic ray driven winds, I don't know how we can really separate this from when we think about the dynamical evolution of the system, this is obviously related to the star formation rate and supernova driven wind. And then we have always to connect these two things.
Absolutely, you have to do controlled experiments where you do one thing at a time. You inject thermal energy, then you inject thermal plus some fraction cosmic rays, and then you see what happens when you allow various damping mechanisms and streaming and diffusion and phase-dependent transport due to ion neutral damping or nonlinear lambda damping, and so on and so forth. So this gets infinitely complicated. But yeah, you're right that at the end of the day, you start with mostly supernovae.
Because you have to share this energy between the between the two processes, right?
Of course, yeah. So yeah.
So we have actually done what you said, which is you can turn things on and off.
I saw your paper, and I actually have a slide on your work.
Okay.
We will probably not have time to get to this.
Right. But the I mean, I think the
let me help you here, just a second. Just a split second.
What I was just going to say very briefly is that it depends on the phase and it depends on the time, because when there are lulls, star formation occurs in bursts, and so supernovae, the feedback from supernovae occur in bursts, and so when you have a burst, then there can be a breakout, hot gas blows out, helps to drive lower density, higher density warm gas, but during the intervals in between, cosmic rays may be more effective.
Yes, I agree. We can always come back to this topic. Maybe we should smoothly connect to. Oh, sorry, I didn't see you.
Can I just ask one question?
Yeah.
It's kind of a more general question, I would say. For these global simulations, when you talk about the transport coefficient here, are you talking about the microscopic diffusion coefficient from pitch angle scattering?
Yes, that is parameterized based on, let's say, PIC simulations or other analytic quasi-linear theory ideas and so on.
For me, it's never been super clear that that is the only transport coefficient these simulations should care about, because there is a lot of under-resolved turbulence that will scatter these cosmic rays on larger scales.
Yeah,
I mean, so I feel like
course grain your simulations, and I know where you're heading. There's a paper, I think you were on it, where there's a super diffusion, right, that comes from simulations that include streaming.
That's exactly right. Yeah,
they're MHD, and then you coarse grain them, and you look at what the effective diffusion is.
Exactly.
And it seems to be super diffusive, which matches.
It's actually comparable. If you write it as a Gaussian diffusion coefficient, it's comparable to the microscopic.
And this answers the question of why do people find progressively larger and larger diffusion coefficients as they look at larger and larger scales. I mean, that's a completely fair game, right? This field is completely open to figuring out really what's going on. So this also plays a role.
Yeah. So what I think is very important is just defining the scales of cosmic ray transport that we're thinking about, that we're simulating, that we're using.
Yeah.
I haven't, maybe I just don't understand this properly, but I haven't seen this clearly illustrated.
So it's possible that what we are going to transition to also will touch upon this, because it's related to the failure of standard confinement models.
I have a very short comment.
Okay.
Very short comment is that we should not limit ourselves to the resonance scattering, and because, for example, we introduced a new process which we called mirror diffusion, and for some range of pitch angles is definitely much more important, and it's important to take it.
I mean, Bell instability is non-resonant.
No, but I'm not talking about the things which are happening in acceleration. I'm just saying traditional thing, turbulence and the propagation of particles. And in this situation, we still have additional physics which is not included definitely in this quasi-linear theory. And it must be there.
No, it doesn't. No. It does solve other problems that I will mention later, related to gamma ray emission from galaxies. So I want to I want to come back to this point that Elliot brought. So it's kind of connected to this discussion. So let me just show you this. What's the primary mechanism controlling the dependence of cosmic ray transport? And I'm just going to show 2 slides to put everybody on literally the same page. So how do we get the dependence of transport on energy? So one way to do this is to look at the relative abundance of boron to carbon. So this is abundance plot of elements in the universe, and there's a dip here. These elements are easily destroyed in centers of stars. So how much boron you have here depends on how frequent so-called spallation reactions are. When carbon runs into hydrogen, it produces boron. So the longer you wait, the more boron you get. And this turns out to be also dependent, this meaning the ratio, turns out to be dependent on the energy of particles. So you can combine these 2 things to get the confinement time of cosmic rays, and therefore you can figure out what this diffusion coefficient is observationally, and this is how it scales with energy. And so now back to this question proper, right? Or do these streaming instabilities explain the scattering rate and its dependence on energy? And the answer is no. It's either that cosmic rays are unconfined by this instability at low energy, or that slope is wrong. And in terms of what Alex was talking about, you could also have turbulent confinement. And does this work? So just one last equation here. If you know the perturbations in the magnetic field, you can, from this simple random walk argument from many years ago from Major Blanford, you can calculate kappa. And then if you assume resonance condition, then you get the same thing that you observe in real world, i.e. this scaling here. And you may want to say, oh, that's awesome, we have an agreement, but obviously we know here, we spent quite some time talking about how turbulence is not Kolmogorov, so that maybe is why there is something missing. If you have non-Kolmogorov turbulence, then scattering becomes inefficient as turbulence becomes very anisotropic. So then you have to start looking at, other ways of studying turbulence to figure out how cosmic rays propagate. And I want to use this opportunity to advertise Philip's Kempsky talk that will be very closely related to this. I don't want to go into more details, but I guess I'm showing this because this is a turbulence conference, so we need to have, turbulence has to keep on appearing on slides, so here it is again. Okay, so basically that is the legitimate question, right? How do we explain, how do we constrain transport by looking at the energy dependence of cosmic rays?
So before, is it switched on?
It's sometimes not switched on.
Hello?
Now it is.
Okay, so before we jump in calculating kappa, I think that it's a valid question to ask whether the transport is diffusive or not. And the super diffusion, some generalized random walk has been already mentioned. But there are things in MHD turbulence that makes it not even, generalized diffusion. It's a different random process. For example, there's asymmetric diffusion, and it's not even currently described as a, the transport equation a la Fokker-Planck. So there is still open question on the very basics. Yeah. And I think one of the useful things to do, if you want to check theories, is we can look at transport, for example, in the solar wind, because you have direct measurements. Yeah. And astrophysics, from astrophysics, it's very difficult to figure out basic mechanisms. Because
there are some interesting examples that I can show you where you can do that. That I don't think have been mentioned since we got here.
Yeah.
Do you explain what you mean by that?
Yeah. So for example, there's field line random walk, right? So you can go and along field lines without any scattering, and you would still diffuse in perpendicular direction. And people sort of assume that it's the same effect if you go forward and backward. Because if it isn't, then you would create, non-Maxwellian distributions, and you put free energy into particles. And turns out that in MHD turbulence, yes, in general, this diffusion is asymmetric. If you go backwards, if you go in forward direction, you have one super diffusion coefficient. If you go backwards, it's a different one. Yeah, the direction of the field. So if you have imbalanced turbulence, even without scattering, so we are not talking about wave scattering here. We're just talking about particles just sliding along field lines. Even in this case, there is this phenomenon which sort of defies explanation in terms of classic transport.
So if we have time, I will show some examples where you could attempt to put constraints on transport and try to decide if it's more diffusive or more streaming based on astronomical observations, if we have time to get to this. Okay, here's another way maybe to constrain transport in general using some global approach by looking at entire halos of galaxies. This has to do with production of gamma rays by cosmic rays. So I didn't say this because I didn't want to I didn't want this introduction to go over 10 minutes, but when cosmic rays run into, let's say, hydrogen, they produce pions. The pions decay, produce other things, one of which is gamma rays. So if you put intense flux of cosmic rays in a very dense region, then you will produce lots of gamma rays. So then you can ask yourself this question, whether these winds, these outflows, actually violate the limits from gamma ray emission. And so this is how it works. I will show you on one slide what the nature of the problem is, and then I will show you a bunch of solutions, and maybe you don't agree with some of them, maybe you do, but it will have at least structured discussion on this topic. So focus on this panel here. Gravity is pointing down, pressure gradient is pointing up, so you can have an outflow. If diffusion is very small, then basically cosmic rays cluster closer here, where density of the gas is high, and you produce lots of gamma ray emission. In the opposite regime, when diffusion is very high, you quickly wash out these gradients. You don't produce a wind, but you also don't produce any gamma ray emission. So there's some sweet spot for the transport that has been argued by a number of people, some optimal range where you can drive the wind without overproducing gamma rays. And overall, it turns out, according to these ideas, that kappa has to be very large, much larger than the reference number that I introduced in the beginning. Okay, so in other words, scattering of cosmic rays on these magnetic fluctuations due to either streaming instability or turbulence, external turbulence, has to be suppressed. And so here's a bunch of possible solutions. You take your quasi-linear theory scattering and you suppress it by 100 times. We don't exactly know why, but that has been suggested. Another possibility is that maybe streaming and heating is enhanced and by relatively strong magnetic fields that would allow you to stream faster. At the same time, it would allow for cosmic rays to lose their energy in a collision-less fashion without producing gamma rays. And you can see that depending on whether you have streaming or not, you get different answers. This is another solution that is related to strong suppression of diffusion very close to the sites of supernovae. So two simulations, one with regular space-independent kappa, and this one here with suppressed kappa. So if you take this balanced stability and you suppress locally diffusion, then you have these very large bubbles filled with cosmic rays, and they will correlate with low-density regions, thereby suppressing gamma ray emission. So there are some ideas on this, and this has been a problem. Lots of groups come up with different solutions to this, including ideas that maybe aging and evolving spectra on the fly could alleviate this problem. But this is something that people have been wondering about, and it's related to the transport of cosmic rays, which is related to turbulence, and it is an unsolved problem. People should be aware of it. How do we solve it? So if you have a solution, then tell us. Elliot has a solution.
I don't have a solution, I just two comments. So one is the problem is we don't have a lot of gamma ray data. The problem is the most severe in the Magellanic Clouds, where it is very possible that the cosmic rays are just efficiently vented by supernovae, and it's not a diffusive process, it's an advective process. So that we don't, I think that's a very viable possibility. The other small comment is that the canonical 10 to the 28 number is actually not the thing that can be measured empirically. What's measured empirically is some combination of that and the size of the volume that the cosmic rays are random walking in. And if you take the size of the volume that the cosmic rays are random walking in to be the size of the disk, which I think is the right thing to do, not the scale height of the disk, then it's about 10 times higher than that, more like 10 to the 29. So that's also just good to know that that's the...
Yeah, go ahead. So
that's it.
So in these other models, so the first one suggests suppression of scattering is consistent with what you were saying. I think you were actually on these papers, right? This paper here that is related to this idea of locally suppressed diffusion, I didn't say this, but in the bulk of ISM here, diffusion is characterized by this classic value of 10 to 28. And yet, this doesn't overproduce gamma rays. I'm here to state the facts. So you could solve this problem by two different ways. You could solve it like this. Also, these simulations, to be fair, don't have a very large extended halo, which would help you, right? Because once these cosmic rays move away, they still have some opportunity to interact with the gas, and you want to get rid of that opportunity by maybe enhancing transport. It's an open.
I have not a solution, unfortunately, but a comment on that. It's just more general comment that this coefficient, diffusion coefficient, may not be really useful thing, in the sense that we have super diffusion, Levy flights. One of the reasons for super diffusion is this magnetic field wandering accelerated perpendicular to the mean direction. Another is when we, for example, combine mirror diffusion and resonance scattering, we also get Levy flights. This is mostly on the scale of turbulence, but if the scale of turbulence is comparable to the thickness of the disk, it's an important effect. It's not a solution, unfortunately, but just should be taken into account.
So what happened to the tradition of approaching the mic? Go ahead.
I just wanted to say we've made some measurements of cosmic ray. I would call them a macroscopic diffusion coefficient if the cosmic rays were being purely diffused by some kind of turbulence. And we were able to turn off and on things like field line random walk. And we also found that you could get these diffusion coefficients, 10 to the 28, just with density fluctuations. So I feel like we're in a bad situation because there's a lot of things we can do to reproduce this diffusion coefficient. It feels like a very weird, degenerate number that keeps popping up no matter what we do.
I think maybe just a cautionary tale is to remember that the Larmor radii of the GeV particles are about an AU, and so there's no simulation of ISM turbulence that is properly characterizing how they interact with the magnetic field. So there's a huge challenge in extrapolating what we can learn from turbulent boxes to the scale separation that actually matters. And I think that's still an unsolved problem of how to do that. So I think these experiments are all interesting to try to understand the transport, but quantitatively maybe not that applicable.
Can I just follow up? I would be really interested to chat to anyone about what kind of numerical experiments we can do to break these degeneracies and understand this process better. I totally agree. Turbulence box is very simple prescriptions for cosmic ray transport. Maybe we understand something, but I'm not convinced.
One of the possibilities is to study what we can do And it is a study not in the global simulations, but in the local simulations, and see how this corresponds to analytical predictions. And then having analytical theory, you can extend it to whatever you want.
How about this one? Can we constrain cosmic ray pressure in the CGM and ICM? And I'm going to show the plot that we've already seen in a second. So first of all, this is very closely related to what we were talking about a second ago, the gamma ray emission. So what do observations and simulations tell us? Here's one representative simulation from a former student of Penn, Soching G, that shows what you get in a fire simulation when you include cosmic rays versus when you don't in a Milky Way type halo. And cold gas is shown in green, hotter in red, and you have corresponding phase diagrams below. And so basic conclusion from these runs, and many people have reached the same conclusion, is that with cosmic rays you get much cooler atmospheres when the halos are dominated by cosmic ray pressure. When the halos are dominated by cosmic ray pressure, which brings me to Xiao and Chen's plots that we've seen before, which is very information rich and helpful. It shows, let me just show everything here on the plot. I hope you can please correct me if I mess this up, but this is my understanding of what's on the plot. So you have density in cold gas as a function of projection in different halos, and dots correspond to individual clouds along the line of sight. Each line of sight corresponds to a fixed projection radius. So for example, this is one line of sight through a halo. There is a lots of scatter here, but that's quite likely mostly because you're looking at clouds that are far away from the center of the halo, and some of them are far, some of them are very close. So if you just look at the outer envelope of this distribution that corresponds to these clouds that are closest to the halo, then you can compare densities of these clumps to what you would predict from, you can compare to what you would predict from the hot gas best fit if these two things are in pressure equilibrium. Okay, and so there is a lot of scatter, but again, a lot of scatter can be just due to projection effects. However, for some of these points, even individual dots belonging to this outer envelope also show some scatter here, here, maybe here. And so the question is there some room for non-thermal pressure support? If this line here corresponded or overlapped with the red line, then you will have a perfect balance and there will be no room for any non-thermal effect. But maybe there is some room for thermal effect, and maybe this is the way to constrain basically these kind of models. So that's an important work. Hopefully we can push it further and get some meaningful constraints, whether we can, eliminate models like this or not. So if you have comments on this and thoughts, then please, Elliot has.
I love this plot from Soching, but it is worth emphasizing. You should think of this as one possibility of what cosmic rays can do. It assumes a constant diffusion coefficient everywhere, same one in the ISM and the CGM. It's completely possible that cosmic rays are there and produce no interesting effect on the gas phase distribution because the transport is different in the halo. I just think this shows the magnitude of the uncertainty in our models of the CGM because of our uncertainty in the models of cosmic ray transport. And so it really motivates trying to understand the physics of transport better to have more robust predictions and to have more observational diagnostics of the kind Mateusz emphasized.
Right. So, by the way, for the connoisseurs, in addition to non-thermal pressure support from cosmic rays, obviously there is turbulence here that contributes to the scatter. Here it is. I said it once more. Turbulence. Okay, any other comments on this? Any other ways to improve this method? Like how can we tease out the non-thermal, truly non-thermal, as opposed to velocity based? Yes.
Can the observational experts comment on what will become feasible in the near future with X-ray observations? Can we because getting better hot gas measurements at lower halo mass would be extremely useful.
I think Xiaowen wanted to say something. I see you nodding. I guess that means yes.
But I'm not an X-ray observer, but I do agree that, I mean, Irina showed LAMP, a slide on LAMP. I guess that's really will complement the study from absorption line probe, although it will still be limited to nearby sources because it is still noise signal limited. But so just quickly comment on this plot. There are certainly possibilities to improve on this. You know, I would just say that you're totally correct that the scatter is large. So right now you can see the number of vertical lines is
laser pointer if you want.
It's okay. We are talking about. I actually don't. We're talking about, you know, at most 20 systems here. Each system we resolved into, you know, at most 5 clumps along the line of sight. In my talk last week, I talked about one possibility is the deep projection along the line of sight. But there are certainly some statistical game we can play that shows that even from deep projection, we can work out the covering fraction of these low density clumps. Right now, the error bar is still very large, but there is room for some of clumps coming out of, you know, not quite on the outskirts, just based on the comparison of the low density clumps at low impact parameter and large impact parameter. Mm-hmm. So certainly we can study observationally, we can constrain turbulence very well. You know, what's left after we account for thermal and turbulent pressure support is left for interpretation.
Right.
But in the near future, we do have the, you know, as long as Hubble Space Telescope continues to operate, we have the chance of increase the sample size by an order of magnitude. So I'm pleading for everybody here, theorists or observers alike, to support projects like that. What we really need is spectral resolving power. Because through quasar absorption line probe, we already have the spatial resolving power. It's a pencil beam survey. What we really need is the spectral resolving power. Right now, only Hubble can do that, coupled with ground-based observation.
Mm-hmm. I just need this one. Yeah, so just to complicate this a little bit more from the theoretical point of view, suppose that we do this experiment where we really subtract off the turbulent motions and account for this kind of contamination to this plot, and there is really very, very little left in cosmic rays. It would still not mean that cosmic rays are not important, because it means that what could have happened is that the star formation that drives the outflows pumped a lot of energy in cosmic rays into those halos, and that energy went into heating, thereby changing the thermodynamics of this system, affecting thermal instability, spectral signatures, and so on and so forth. So just because you don't see at the current epoch the evidence for the presence of cosmic rays doesn't mean that they didn't do their job before, prior to disappearing, right? Their energy can be expended on other things. Yes.
So I have just a final comment regarding when we go back to the galaxy scales, that Lazo has observed gamma rays at TeVs in gigantic halos around pulsar ring nebula and star clusters, and we have no idea how those gamma rays are produced so far. There is this issue with the cosmic ray transport, confinement near the source and propagation. Mm-hmm. And the model so far does suggest that you have you need values for the coefficient for kappa, you know, at least 10 times different compared to the interstellar median average value, and it has to change a lot, vary a lot from the source to the more diffuse gamma, and a possibility. I mean, we really need to improve the theories on cosmic ray transport, and one of the possibilities is really to get into this super diffusion combined with the mirroring and bouncing that Shu and Lazarian have been studied recently. And I can add that we have been performed numerical simulations experiments that show that you have this enhancement in kappa of a factor of 10 or so, but of course these numerical experiments are, you know, MADD simulations with test particles are still in progress.
Yeah, I agree. There's enormous uncertainty in kappa. I would go even further to say that there are other models that predict kappa on the order of 10 to 36 centimeters squared per second, all the way to 1 millionth. So it's, you know, it's a huge dynamical range.
Yeah, let me just comment on that, which is there isn't a standard value in the interstellar medium. So the, you know, in particular, in the neutral gas, the scattering rate is incredibly low because ion neutral damping is very effective. So, you know, it's like the scattering rate is like 10 to the minus 30. Kappa is, you know, 10 to the 30. So the scattering rate is extremely low where, you know, in the region where the cosmic rays are actually interacting with any significant amount of matter. Then in the ionized gas, which has lower density, that's where the, you know, kappa drops and sigma increases. So there isn't a single value by any means. No. It varies by orders of magnitude.
High energy gamma rays, this has been a puzzle really. For very, just to comment that for very high energy gamma rays, of course these observations are very recent, but it has been a puzzle.
All right, Irina has a question.
Just to address Salet's question very quickly, we have data for doing that. In fact, we have measurements. We don't know how to interpret them. Okay, so I've advocated for quite a while to have some models that include, do not include cosmic rays and all the additional physics, having step-by-step approach. It's difficult to model in context of clusters, galaxies. All right, let's start with idealized boxes. That's a huge step forward. We have the data, we can do that. We can measure it in large samples of galaxies, clusters. We're mainly showing clusters, they're simpler at this stage, but galaxies is easy to extend. Moreover, we have data coming that will also show radial variations of clumpiness and density fluctuation, not just one number. We can also look at some radial information, which I believe will be very important for cosmic ray transport. So data out there. I really encourage theorists here to kind of sharpen a little bit their message and show us whether there are indeed some interesting testable predictions, even if these are just constraints. I think those are important. Yeah.
Thanks. Okay, so I'm torn right now because I am thinking of going into two different directions, and we could have a democratic vote which way to go. Unless, Peng, you want to add something, because it seemed like you were...
Is it stacks for the galaxies? Or what are you referring to? Yeah, is it stacked X-rays, or what constraints do you have?
Well, I mainly refer to quite massive galaxies where we can detect individual halos, but stacking is certainly an option, especially also with Irazita data being released. That's a natural step forward. Yeah.
Does it include star-forming galaxies?
No.
All right, so I am torn between two topics. Both of them are related to transport and tangled fields and things of that nature. One is the issue of bottlenecks. I can explain to people who don't think about this too much what they are. The second topic that I'm thinking of is whether we can constrain transport by looking at individual objects. For example, one supernova, or one little so-called HARP in space, or one molecular cloud, or something like that. Everything that we talked about so far was, you know, looking at large CGM, halo, gamma rays, motions in space, but now we could also talk about individual objects. maybe we should do that, unless, okay. Oh, we should, oh yeah, okay. We have 12 minutes, so we could actually do both. So who wants to talk about this? This is related to things of that nature.
Individual objects first, raise your hands. Pretty strong, okay. Let's start with this, and then I want this, so we're starting with this.
Fearless leader, follow your order. Okay, so people have been doing these really cool hybrid peak simulations of cosmic ray acceleration in individual supernovae. They looked at Fermi process, acceleration of these non-thermal tails. They've been looking at how cosmic rays get confined to the sites of supernovae explosions. So it turns out, if you haven't really been following literature on this, that acceleration of cosmic rays across the shock front depends on the orientation of magnetic field. If the fields are aligned with the direction of the explosion, then particles have easier time crossing back and forth, and they get boost every time they get a head-on collision as a result of Fermi-like process. Versus in the opposite case, not much is happening. So if you take a supernova and put a magnetic field through that explosion, then you could expect to have these polar regions that light up as a result of acceleration of cosmic rays. And you can then compare predictions from such a model to X-rays, radio, and gamma rays, as done here. And you can do a little bit better. So this is something that I recently learned about, which I thought was pretty cool. You can define this obliquity angle, and this arrow here, the longer arrow, represents the direction of magnetic field. So it is at these locations here that you expect more acceleration of cosmic rays. You can expect radiation from here, and you also expect effective gamma ray, effective adiabatic index to be lower than the regular 5/3, like as in the regular ISM. It will be closer to 4/3 because that's now populated with relativistic particles. So when you have that, the gas becomes more compressible. And so people looked at compressibility as a function of this obliquity angle and compared compression rate ratio to obliquity angle to these models. And it's, I think, a beautiful example of how some of these ideas to do with acceleration actually work. Obviously, these are data points, and this is a model. So this is one maybe success story. I want to tell you one additional success story related to
Is there independent constraints on the magnetic field direction to confirm the interpretation?
The question is if there is, I have a microphone here, if there is an independent constraint on the orientation of magnetic field in this object. The answer to this question is, I don't know, but there may be. But this is still quite intriguing, actually. Well, you measure gas density in a pre-shock region where the shock hasn't actually gone to, and immediately behind it, right? So from Rankine-Hughes condition, for strong shock, it will be 4. For strong shock that is going through a medium that is characterized by lower adiabatic index, it will be more than 4. 4 is what you get from 5/3, the classic result from the textbook, right? Okay, so this is a success story. Here is another success story before I kind of, throw cold water on some of these ideas. So this is a beautiful image from Meerkat. And right here, there is this thing that people call HARP. And it's a bunch of presumably vertical magnetic field lines. And there is some source of cosmic rays that is going through this in this direction, from the left to the right. At some point it was here, it injected cosmic rays, they started moving along the magnetic field line, then that source moved a little bit to the right and did the same thing, and cosmic rays moved a little bit, but not as far as in this original case, because obviously less time has passed at this location. And this process creates this thing that people refer to as a HARP. So why is this related to any of this thing here that we're talking about? Well, you can clearly see that this is an example of cosmic ray transport. Cosmic rays are being transported out. So then you have all these fancy ideas, streaming, diffusion. Which of these models works better? right? And so this was done by friends of mine. Timon Thomas was on it, and Christoph Frommer, and they basically did a 1D calculation of what you get when you do streaming plus diffusion versus just diffusion. And the zigzaggy black line is obviously the data. The smoother lines are simulations. And it seems that this case matches results better. You have a streaming plus diffusion, as you would expect if you have, for example, streaming due to streaming instability plus some damping processes of whatever nature that would actually make the transport a little bit faster than streaming, and added some diffusion component to it. So that's consistent with these ideas. It's consistent with our incomplete understanding of the process, because obviously we know, as we discussed earlier, there's, these models still predict wrong dependence of transport on energy, for example.
Excuse me, I have a question, but this should be a signature of relativistic electrons, right? Not protons.
That's a good point. I mean, obviously, what you're looking at here is radio emission, where it comes from leptons. But leptons, you can also
you have to assume you can
create leptons by collisions of protons with ambient medium.
Yeah, but anyways, it's an assumption,
yes,
right? Okay.
Okay. So this isn't nice, but I'm going to leave you with this. The simplest problem you can possibly imagine. There is a cloud of gas in space, and supernova goes off nearby and illuminates the cloud. And you're calculating here ionization rate as a function of column density in H2 in that cloud. And this is the data here. And then you can go back to the beginning of this discussion. I showed you this picture of the spectrum of cosmic rays with the low energy part highlighted in red. These are the low energy cosmic rays that can change the thermodynamics of the ISM. And we got them from Voyager 1 and 2. They are unaffected by solar modulation. If you start with the spectrum and you let cosmic rays just go on a straight line, according to the so-called free streaming approximation, then you get this line here, which is, at least an order of magnitude off compared to what is there. So I would say, we don't really understand how to solve the simplest possible problem when you have just one cloud exposed to cosmic ray radiation, and that's terrifying. So the previous ones were success stories. This one is not so much. If anyone wants to comment on this, that's fine. I just wanted to have, go.
Spectrum.
Oh yeah. But the thing is that
there are different assumptions about the spectrum.
Yes. If you go to other lines here, they don't match results from Voyager data. Only this one, according to this paper, matches the data from Voyager.
There's other issues.
Multiple. The other issue is that this model assumes that cosmic rays go in a straight line, versus what will happen in a model that kind of fits our understanding of streaming, is that basically the propagation of cosmic rays into that cloud can be suppressed as a result of you can be basically scattered sideways, and this assumes that there is perfect penetration and you just go along the straight line. That's a gross approximation. So there are multiple issues about this. We have 3 minutes. I just want to do one thing. I was sitting in the back yesterday, and I am curious. This is kind of a philosophical comment. Maybe don't quote me on this, but it's getting recorded anyway. So when people when people look at spectra to constrain astrophysical processes in space, they compare those spectra to the spectra that were produced in a lab setting. We didn't really constrain transitions in, let's say, iron by looking at the sky. We used lab experiments to make these comparisons. So is it possible that we are faced with the same challenge, that basically we will be forced to go into the lab and then compare or make predictions for transport processes in a lab and then test them in a lab and then compare them to observations. So when I was sitting in the back, I found these I prepared this collage of papers that have relevant titles. I'm just going to, I know we've been here for an hour, so I'm just going to read it to you. Transport of high energy charged particles through spatially intermittent turbulent magnetic fields. Highly relevant, tested in a lab. Laboratory evidence for dynamo amplification of magnetic fields in a turbulent plasma. Highly relevant. This one, so Irina just talked about clusters and viscosity. I think she just left. So when she comes back, I will repeat this part. Strong suppression of heat conduction in a laboratory replica of galaxy cluster turbulence plasmas. So she talked about viscosity, but it's linked to conduction, and this is what you can actually test in a lab apparently, using laser experiments here, laser plasmas. So I'm going to leave you with this thought because I'm 10 seconds late, and you said if I were going to be 1 minute late, there would be consequences. So I don't want to face the consequences.
Well, thank you very much.
Yeah.